welcome. Dear friends, a very warm good morning to all. We are gathered here for attending the national webinar Glimpses of Ancient Indian Mathematics, organized as a part of the ongoing webinar series Math Ecstasy, organized by Maths Aspirants Groups. I extend my wholehearted welcome to all. Before moving to the session, let us begin with a prayer. I invite Miss Anjali from Cochin University of Science and Technology to present the prayer. Over to you, Anjali.
Maitrim bhajada akila hrijetri. Maitrim bhajada akila hrijetri. Atmavadeva parānavi pashyara. Atmavadeva parānavi pashyada. Yuktham tyajada, spardham tyajada, tyajada parikshat pramamam pramanam. Maitrim bhajada akila hrijetri. Maitrim bhajada akila hrijetri.
Thanks, Anjali, for the nice prayer. Your voice catched all our minds and led us to some level of spirituality. Math Aspirants Groups is an initiative of Dr. Vinod Kumar P., Assistant Professor of Mathematics, TM Government College, Tirur, Kerala, started on 2017. It's a community of math lovers, students, faculties, research scholars. Apart from providing a discussion platform, it organizes several online problem-solving sessions and online test series to help students who prepares for competitive exams like CSIR NET, JRF, IIT JAM, NBHM, TII for entrances, etc. Also, Math Aspirants organizes national webinars on different frontier in and around mathematics to understand and relish the beauty of mathematics. Now, I request Dr. Vinod Kumar sir to say a few words. Welcome, sir.
A warm good morning to all. The quotes from Vedanga Jyotisha, which is a subtext of Rigveda, which can be translated into English as are the crestes on the heads of peacocks, as are the gems on the hoods of cobras, so is mathematics at the top of all sciences. These quotes rightly conveys the attitude and the richness of Indian tradition of mathematics. Today's webinar is a great milestone in the journey of Math Aspirants Groups, and it is a long cherished dream to arrange an expert talk on ancient Indian mathematics. I'm sure that today we have the most right person to deliver such a talk. I thank Professor Abhishek Adhikari of Presidency University, Calcutta, for introducing me to Professor Parthasarathi Mukhopadhyay. See, in order to arrange a technical session in mathematics, it is a little bit easier compared to arranging a popular talk in mathematics. I don't know how many of you are aware about the difficulties in finding a right person for a popular talk in mathematics. It is really a tough game. For this topic, I am sure that I succeeded in that game. You will definitely agree with me after attending today's intellectual feast that is going to happen in the next few hours. In this occasion, I would like to express my sincere thanks and gratitude to Professor Parthasarathi Mukhopadhyay for accepting our invitation and joining with us. And I am very much grateful to you, sir. I take this opportunity to thank all my teachers, friends, students, well-wishers, supporters for their supports and blessings in my way. I am very much indebted to my friend Dr. Bijuman R., Associate Professor and Head, Department of Mathematics, MG College, Iriti, Kerala, for all the technical helps and support from the very beginning of Math Aspirants Groups. I would like to express my gratitude and love to Professor Abhishek Adhikari, Calcutta, Professor Ambat Vijay Kumar Sir, Cochin University of Science and Technology, Professor Prajit, Malabar Christian College, Calicut, for being with me with their support in all the initiatives of Math Aspirants Groups. Also, I express my deep love and gratitude to Ms. J.R.O.S. Johnson, Research Fellow, IIT Madras, for all the supports in all my initiatives. Warm thanks also go to Ms. Anne-Marie Tony, Research Fellow, Cochin University of Science and Technology, for being with me throughout. I take this opportunity to thank Ms. Tidhi Bishwas, an MSc student from NIT Trichy, Ms. Namrata, an MSc student from Manipal Institute of Technology, Karnataka, and Ms. Amrita Warrior, a BSc student from St. Joseph College, Devagiri, Calicut, for their support in arranging this webinar. I hope that the session ahead will be really fruitful and inspiring to everyone who loves maths. Thank you.
Thank you, sir. Friends, today's webinar on ancient Indian mathematics is fourth in the Math Ecstasy webinar series. The previous webinars are on role on mathematics in cybersecurity by Professor Abhishek Adhikari, Presidency University, Kolkata. Artificial Intelligence, Myths and Realities by Professor Chandrasekhar Lakshmi Narayan of IIT Palakkad, and Beauty of Complex Analysis by Professor Ambed Vijay Kumar of Cochin University of Science and Technology. Friends, as all of you know, India has had a long legacy of extraordinary scholars who had immense knowledge and about mathematics, astronomy and other disciplines, even though its reputation suffers from egocentric bias of history. India has a rich heritage of mathematics. Today, we are really blessed to have one of the most apt and wonderful personality to speak on this topic, Professor Parthasarathi Mukhopadhyay from Kolkata. I request Professor Ambed Vijay Kumar sir to introduce our speaker.
So, very good morning and warm greetings from Cochin. Before I come to the formal introduction, let me briefly tell you about this unique project initiated by Dr. Vinod Kumar for the past, I think, at least 2 years I am aware of. It is also interesting to note that he has dragged in young math aspirants in the organizing team, consisting of Dr. Bijumohan from a college in North Kerala, J.R.O.S. Johnson, who was our master's student in Cochin University, now a PhD scholar in IIT Madras, and Anne-Marie Tony, who did her master's from CUSAT, and she is continuing CUSAT as a research scholar, and Namrata from Manipal Institute of Technology, Karnataka, and Amrita from St. Joseph's College, Devagiri, Calicut, a BSc student. So he's doing a great service by way of introducing several speakers to the national level students and introducing some youngsters as potential speakers for training them to national level tests. As far as I know, this is a unique activity in India. And there was earlier a project called National Initiative on Math Education, which was led by Professor Ramanujam of Institute of Mathematical Sciences, in which Professor Partha Mukhopadhyay and myself were also involved. So this is another phase of cultivating interest in mathematics or popularizing mathematics through the youngsters so that they know what had happened in the history, not only history of India, history of mathematics in India, but history of mathematics itself. And there are not very many people to talk about the history of mathematics both in India and abroad. And for the benefit of students, let me tell you that there is a event called International Conference on Communicating Mathematics. Okay, and this is going to be held in next year, 2022, in some part of the Europe. So several mathematical activities are going on all over the world, and thanks to the technology now available through internet and all that, and because we have more holidays now, not both HOLI, holy day and holiday. Okay, both are there. So we have enough time to spend a few hours with those who are interested in hearing mathematics. So I have great pleasure to introduce my good old friend, Dr. Partha Mukhopadhyay, who did his master's, MPhil and PhD from University of Calcutta. And he is also the person behind the translation of the great book on Srinivasa Ramanujan by Robert Canigal, entitled The Man Who Knew Infinity. I had the taste of this process because though I was not a formal translator to Malayalam, I was a consultant for the Malayalam translation of this book. And for a personal collection, I collected books from all Indian languages so far published. It's in my library, personal library. And that opportunity gave me to know inside and outside of how great Srinivasa Ramanujan was. So it was Malayalam book has second edition now. Even the second edition is sold out. So we are going for the e-version of this book. It's almost ready. It is published by the Kerala Language Institute. Today, Professor Partha Mukhopadhyay is going to talk on glimpses of ancient Indian mathematics. As you all know, no discussion on Indian mathematics will be complete without mentioning the Kerala School of Mathematics, which existed in the banks of Bharatapuzha. The place, some of the places near the banks of Bharatapuzha is the place where Dr. Vinod Kumar comes from, Tirur, Angadi, Alatiyur and such places, which was there during 1350, 1650 period, which we call the golden age of Indian mathematics. And there are plenty of books and literature available on Kerala contribution to mathematics, ancient mathematics. Obviously, we should not forget the great names of Aryabhata, Pingala and others, Brahmagupta. All these people, I think, I am sure Dr. Partha Mukhopadhyay will be discussing all these things. One thing which I want to tell about the personal thing that Dr. Partha Mukhopadhyay did was creating a video show on the genesis of the zero. Zero is a very dangerous idea. There is a book by name Zero, the biography of a dangerous idea. See, usually people write biography of living things. Okay, you don't write a biography of a table. The title of the book is Biography of a Dangerous Idea, means zero is living. Okay, zero is a living object, because without zero, we people cannot, any human being cannot do anything without zero. Some are interested in getting zero marks. Some are getting interested in double zeros preceded by 1. So zero plays a wonderful role, and I take this opportunity to congratulate Dr. Partha Mukhopadhyay for his wonderful video project on the genesis of zero. And I'm happy to formally invite Professor Parthasarathi Mukhopadhyay for his, I'm sure that I've heard him earlier, so I'm sure that this is going to be a very good Sunday, and wish you all the very best, and invite Professor Parthasarathi Mukhopadhyay for his talk.
Thank you, Vijay Kumar sir. Now, without any delay, let me welcome our research person. Over to you, sir.
So did I for his kind introduction, and Professor Vinod Kumar as well. A warm welcome, very good morning to everybody from Kolkata. So today we will talk on glimpses of ancient Indian mathematics. I'll just switch over to the presentation mode. So before I begin the topic exactly, I think one or two words on the whole issue as such. The idea is to talk about glimpses of mathematics in ancient India, because you see the entire body of available knowledge of ancient Indian mathematics. It's a huge repository. So there are different ways on which talk can be arranged on such a topic. One of the way will be to make a very commendable list, long list of claims of certain facts and results that is usually ascribed to the ancient Indian mathematicians. But I usually refrain from this particular approach of presentation in a talk because it sounds like a tall claim. One very unfortunate thing that I would like to mention, which is really, really unfortunate for people like me who are students of ancient Indian mathematics, that this is somehow hijacked by Indian politics. Without getting into much controversial points, I think I can mention this as a mere statement of fact that there are two camps, one of which claim everything was there in India. The other camp says there was nothing. So it is actually very important to analyze objectively, to know exactly what was there. And whatever little bit I have gone through, my impression is not an iota of braggadocio is needed. It was such a wonderful knowledge system. It was such a wonderful amount of tremendously deep mathematics that was dealt at that point of time. But if we can really unearth that, if we can really talk about that to our present generation students, this will be really, really something, not to leave on that, but this will be really something worth knowing, to motivate yourself to pursue your own present skill and your pursuit of mathematics. So said all this said and done, let me talk about certain aspects of this ancient Indian mathematics, and I would like to begin with this quote from Manjul Bhargav, who surely you know that he is a professor at Princeton University, the first ever Fields medalist of Indian origin. And in 2014, in Times of India, Manjul said this: students in India should be taught about the great ancient Indian mathematicians like Panini, Pingala, Hemachandra, Aryabhatta, and Bhaskara. You see, amazingly, these names, I'm sure you have heard of Aryabhatta, Bhaskara, some perhaps of Hemachandra, but Panini and Pingala, you see, Manjul is ranking them as mathematician. Why? Panini may be known to you as a grammarian, that he was actually, and Pingala is a prosodist. But Manjul, is actually placing them in the same level with Aryabhatta and Bhaskara as mathematician. Why? And he further says, their stories and works inspired me, and I think they would inspire students across India. That's the more important part of it. They would inspire students across India. If we know our past, it is not for living in the past. That will be wrong thing to do. But that certainly can be an inspiration. These can be role models for us, that what we actually achieved at that early period of civilization, that can be an inspiring fact for us to pursue our own journey of mathematics. That's the most important relevance of this kind of topic and talk as far as I am concerned. He further says many of these works were written in Indian language, and Sanskrit of course, most of the cases. If you go back to that ancient period, in beautiful poetry, and contain important breakthroughs in history of mathematics. And you see, coming from a Fields medalist, that these contain important breakthroughs in the history of mathematics. It is not just certain, scattered results here and there. They are being categorized as breakthroughs. In another interview, Manjul was asked to name 5 of his most favorite books. And you see, the first book he mentioned is the Sulva Sutra by Bodhayan. And it goes back to 800 BC. Look at the time period. And what he says is this: perhaps this is the first place where Pythagorean theorem comes up. Pythagorean theorem is very well known to every student of, high school mathematics. That right angle triangle, its hypotenuse and side and all that thing. But time of Pythagoras is 5th century BC. And here we encounter a 8th century BC text, Sulva Sutra, by one Bodhayana, where a trace of Pythagorean theorem can be found. Just learning geometry there in this artistic way is something that I think India should bring back. So we'll try to throw some light on them. as I told you, I am not going to make a big list of the claims of this was there and that were there. Rather, I would like to dwell upon one or two issues, get into it at a certain depth, and try to analyze and understand what exactly is the merit of this particular claim. I'll just pinpoint very few hand-picked, chosen issues, mathematical issues from ancient India, and try to dwell on it at a deeper level, rather than making a long claim. That you can always, check in the Google or all these available repositories. But there you won't get this deeper discussion, which I think is important mathematically. Not just to know the name of the work, but to know exactly, in terms of today's mathematics, what exactly did these people achieve? Translating their work in today's language, exactly how far did they go? I think that will be the central theme of today's discussion. The second book was Chanda Sutra by Pingala, the prosodist from 2nd or 3rd century BC. And it's a book on prosody. It's not a mathematics book. But you see here, you find problems that are being dealt with at ease that leads to fantastic, deep mathematical algorithms of combinatorics, binary to decimal and decimal to binary conversion, work that leads to so-called Fibonacci sequence. Do you know the time of Fibonacci? Leonardo Pisano. His book was written in 1202, Libera Bacchi. And this gentleman, this year, Pingala, his time is 2nd or 3rd century BC. So about 1500 years before the time of Fibonacci. And here you see the seeds of Fibonacci sequence, which latter was further developed by people like Hemachandra, whose name you found in that list of Manjul. Then comes Ashtadhyayi of Panini. Again, that's a book of grammar. It's a Sanskrit grammar text, one of the most fundamental and most important worldwide. But you see, the way this analysis of grammar was done, it is so very mathematical in nature. After all, mathematics is not science. Mathematics is a language. It's a language in which science speaks. So that at a deep-rooted technical level, there is a similarity of mathematical logical development, the thread of that logical development, along with what Panini did as a logical development of grammatical analysis of the language. It laid the foundation of classical Sanskrit. And then came two other books, one of which my good senior friend Ambat has already referred, The Man Who Knew Infinity, one of the most inspiring life story, and there's another fantastic book, Gödel, Escher and Bach. So I'll just try to draw your attention to the first three books, Sulva Sutra by Bodhayan, Chanda Sutra by Pingal, and Ashtadhyayi by Panini. So today, the time that I have, I'd like to dwell upon initially with the Sulva Sutras. Just 1, 2, 3 Sulva Sutras I will try to explain to you, to tell you the beautiful geometry that was there. You see, it is told everywhere that we have learned geometry from the Greeks. There's Euclidean geometry, that is what we learn at this beginning level. Everywhere in the world, the school level, geometry is the deductive, beautiful arguments of Euclid. So that is 300 BC. And here we have a text, Sulva Sutra. Sulva means cord, rajju, knotted cords by which measuring was done at that period of time. Measuring what? I'll come to that. But that led to some geometric ideas. And that led to the sutras, Sulva Sutras. The nice geometry of that which predates Euclid by at least 500 years. And what experts has to say on that. We'll come to that. But one rudimentary word of caution, that when we talk about India, in antiquity. The word India, it does not refer to the modern present day Indian geographical map. That you have to bear in your mind. When we talk about the ancient India, it actually encompasses the whole subcontinent, right from Afghanistan to Myanmar, Burma, Indonesia, and the whole place. So things of Indian origin, some of them may, as per the present day geographical situation, may be located in the present day Pakistan, something maybe in present day Burma. But usually in literature of ancient mathematics, they are referred to as Indian contribution. So that must be made clear right at the beginning. And these are some of the ruins of those ancient learning centers: Nalanda, Takshila, Vikramshila, so on and on. There are so many. All were destroyed, plundered by one after another foreign invasions. Takshila, as you can see, look at the time, 1000 BC to 5th century CE, having a university kind of thing in 1000 BC. And the location of Takshila is it's in the Gandhara region, which is somewhere, the present day reference will be Afghanistan, Pakistan-Afghanistan border. And then you have Nalanda, of which you might know more about that. So these are some learning center of learning at the ancient India. And this is a very incomplete list of some of the great names of ancient Indian mathematics. This division that I have made in BC and AD, this is absolutely my own choice. And as I have already mentioned, it's utterly incomplete. There are many other names. I have just pointed out some of the salient names. To start with this Sulva Sutra people, Bodhayan, Apastamba, Kattayan, from 5th to 8th century BC. Then Panini I have already pointed out. Sometime between 5th and 7th century BC, Pingala 2nd or maybe 3rd century BC, Chanda Sutra. And then comes Bhakshwali Manuscript. If time permits, I have an intention to tell you something about Bhakshwali Manuscript mathematics as well. Such wonderful mathematics. I mean, it's really frustrating for me, or people like me who are trying to pursue this ancient Indian mathematics, that how little do we know actually of the mathematical treasure of these kind of things. How many of us really know what exactly is there in Bhakshwali Manuscript? There is no system in our country, nowhere, at no level, neither at the beginning nor at the end. You may have a master's or PhD in mathematics, but there is simply no scope anywhere else that you come to know about the fantastic and deep mathematics that was there in this manuscript. So if time permits, I have an intention to tell you something, a little bit, of Bhakshwali Manuscript mathematics. And then, of course, the Aryabhata of Kushumpura, Bhaskara, Brahmagupta, of which the mentions have already been made, and then the great Kerala school of mathematics. Starting with Narayan Pandit, Ganit Kaumudi in 14th century, Guru Madhava of Sangamagrama, though none of his texts are extant, the Venovaraho and Sfuto Chandraptri, none of the texts have been found, but all the disciples of Madhava, Parameshwara, Nilakantha, Jeshtadeva, his great book, Yukti Bhasha, and even, it transpired ultimately to such a ground-to-earth level that these books ultimately were written in the local Malayalam language. And now their translation in English, they are all available. If you are interested, you can see that at least 200 years before calculus was invented, how this expansion of functions by pure trigonometrical technique were done by these people. The Gregory series, tan inverse, now it is called Madhava Gregory series. And there are so many others. Unfortunately, I don't consider myself an expert on the Kerala school of mathematics. There are other people who have studied at depth. I am studying them right now, but not having a command on that so that I can get into the greater depth of that. It's really amazing, fantastic mathematics. And once again, I'd like to tell you that particular fact that, when we talk about these things, we, in the sense of people who are talking about ancient Indian mathematics, we don't invite you people, the young learners, young listeners, to do mathematics exactly in that way today. That may not be judicious. But to know these amazing, wonderful facts that these achievements were made so early in our country by these seers, it will be tremendously motivating for a young learner to motivate himself or herself to pursue his own research, his own achievements. And there lies the relevance of knowing this ancient Indian mathematics, and that from true perspective. No mumbo jumbo, no braggadocio, no false claim, but objective study. And this history does not mean only, the time frame, which century, who lived and what. No, not the list of names, but the mathematical history. History here means translating their mathematics in the present day language so that we can connect and appreciate exactly what has been done at that early period in our society. So coming to the idea of Indian system, I mean, no talk on ancient Indian mathematics can be, accomplished without mentioning this most precious and most fundamental idea that was gifted to the world by India. The decimal place value system in tandem with the numeral zero. The invention. It's not a discovery. Zero was an invention. It was invented. There are many claims and counterclaims of some other civilizations like Greek civilizations, Chinese civilizations. And it's a huge long story. See, if I want to talk about zero, I can talk for 3-4 hours at a stretch. But today, I am not going to talk about zero. I just mention it because, the whole story of zero, it's like the sun in the morning sky. It, appearance of sun actually does not allow you to see the other stars and planets in the daytime. The story of zero is so influential and so amazing that it actually does not allow you to see the other amazing feats that were achieved in ancient India. So today I'm not getting into that. I'll just touch upon the issue of zero and give you certain references. If you are interested, you can check from them, get into the greater details, deeper ideas of this story. Right now, there is a fantastic international conference that is going on. It's by one organization in Amsterdam. It's called Zero Origin India. And they are having a zero project. Every Sunday, they are having a talk on that. This will be a 4 months affair. And all, experts from all over the world are taking part in that to fix this different controversies that still are there about the actual origin of the number zero. Of course, India is a very strong stakeholder there. Anyway, I'm not again getting into zero. This is something that has already been mentioned by Vinod Kumar. This Jatha Shikha Moiranang Naganang Manayo Jatha Tatha Vedango Shastranang Ganita Murdhani Sthitam. It tells about the seat of mathematics in the ancient period of India, in the Vedanga Shastra. 6 limbs of Vedas: Shiksha, Talpa, Vyakarana, Nirukta, Chanda, and Jyotisha. Now, this Jyotisha is calendrics. And in this calendrics, where you have to calculate the exact time from performing rituals, as those days they believed that this exact time is very important to perform the ritual if you want to get the fruit of that, yagga or whatever ritual is that. The exact time is needed. That particular time you have to perform the ritual. And that is why this calculation, the precision of the calculation was tried to achieve, and that gave rise to this mathematical precision, mathematical computation of this Vedanga Jyotisha, right? So, before leaving zero aside, just to share with you one joke that I got from social media, and that in the form of a common misinformation, unfortunately. It's about Aryabhata. This is an imaginary figure of Aryabhata, as you can see in the front of Ayuka in Pune. The popular joke, it says that one day Aryabhata asked his wife, "Will you allow me to spend the night out with my friends?" And the wife says, "According to your calculation," you see, you are a great mathematician, so do your calculation yourself. What is the probability of my giving consent to this? And it is then Aryabhata invented zero. I know everybody, start after, reading this. But what I find unfortunate in this whole humorous thing is that this is a complete misinformation. Aryabhata didn't invent zero. Aryabhata's at least 700 years before Aryabhata, in the Pingala Chanda Sutra, there's a specific reference to zero. Rupe Shunyam and Vi Shunne. there are these two sutras in 8th chapter. But once again, I am not getting into the details of that. I just refer to you that this great mathematician Aryabhatta, he didn't invent zero. He used zero in his fantastic calculation of square root and cube root algorithms. One important result of Aryabhatta, because the name of Aryabhatta is mentioned and he is Aryabhatta, not Aryabhatta. There's a difference between these two clans, Vata and Vatta. So he was Aryabhatta and his book is Aryabhatiya. And this Aryabhatiya, one fantastic result out of so many is this one. This is telling you the approximation of pi. It says Chaturadhikam Satamashta Gunam Dvashashtis Tatha Sahasranam Ujutodaya Vishkam Vassa Ashanna Vritta Parinaha. This I got from Ram, one of my good friends in IIT Bombay. See here, in 499 AD, look at the time. He is telling you this verse, which tells you, it's not difficult. If you are not conversant with Sanskrit, please don't be, afraid of Sanskrit. It's a very simple language. Chaturadhikam. So it's 4 more than 100. Satam. Sata is 100. So 100 plus 4 as it is written below. Ashtagunam. So you are multiplying it by 8. Ashta. Then Dvashashtis Tatha Sahasranam. Shashti is 60. Dvashashti is 62. And Sahasranam is 1000. So you are just adding 62,000 to this number. And you are getting a number in the numerator. But what does this number tell? The number tells, go to the next line, Ajutodaya Vishkambhasya. Now Vishkamba is the diameter of a circle. And Ajuta is 10,000. So Ajutodaya is 20,000. So what this number? It is the Ashanno Vritta Parinaha. So Parinaha is the circumference, the length of the circle. And this length of the circle, which circle? The circle that has Ajutodaya Vishkambhasya. That is 20,000 unit is the diameter. Then its circumference, the length of the arc of the circle is given by the number in numerator. Now if you apply your present day idea of 2 pi r, where 2r is this 20,000, and the numerator should be the circumference which is 2 pi r, then you clearly know that this quotient 2 pi r by 2r is going to give you the value of pi, and that's what it is. You just do the calculation, you see the value you are getting is 3.1416. So that was Aryabhatta. It's much advanced than just talking about zero. It was known to him. It was known to that civilization for more than 700 years by that time. They are doing much more complex calculation by that time. And the most important part of this whole thing is the word ashanno, approximate. Not just 3.1416 is the exact value. Even that was known to them, that this value is approximate value. That precision they could attain at that early point of time. But that's Aryabhatta. So let me leave Aryabhatta. Let me leave zero with this reference to you that if you're interested, there is a 1-hour lecture in YouTube that is available. It was a lecture given in IIT Gandhinagar in one of the international conference, Zero and Eternal Enigma. Over 5,000 viewers have already hit that. So if you are interested, you can check with my name in YouTube. You will find this 1-hour compact video telling you about the natural history of genesis of zero. And as Professor Ambat just pointed out, very recently this year, we have instituted a zero gallery in my institute in Calcutta. If you ever visit Kolkata, you are most welcome to come to Narendrapur, Ramakrishna Mission Residential College to visit this gallery. This is about, this gallery showcase the whole story of inception of zero across 5,000 years of human civilization over all the ancient civilization, not just India. India is an integral part of this, but there were other civilizations starting from Egyptian, Babylonian, Mayans, and on and on and on, Greek, Chinese. Every civilization has been addressed, their own numeration system, their idea of having zero or not having zero or zero-like concepts. In what sense it is said that the Indian zero is the true progenitor of the modern zero? Why is it not the other zeros? All these are addressed and showcased in the Zero Gallery, where you are most welcome whenever you visit Calcutta. And a book is also there if you are interested. Much Ado About Nothing is in English. Is a supplementary book to that gallery. It's available in the e-commerce, the Flipkart or Amazon or things like that. It's a fantastic book. I recommend, if you are interested in knowing about the natural history of zero, this book may help you. And leaving this zero story aside, now let me talk about the idea of Sulva Sutras, the origin of Indian geometry. And may I point out again that this is much older than the time period of Greek geometry that we know. Now this idea of geometry, as you know, in Egypt, it was due to the recurrent inundation of Nile. The lands were flooded, and to measure the land again, to redistribute the land to the actual owner, the geometry flourished in Egypt, ancient Egypt. But in case of India, it was the fire altars, the Vedic fire altars and their exact construction. That was the reason for flourishing of ancient Indian geometry. And these rules actually evolved to the general enunciation of geometric rules that we find in Shulva Sutras. Shulva, as I told you, these are knotted strings. Those strings were used to measure exactly and construct this kind of altars. There were so many. This is only one that you can see in front of you. This is called Srinachiti, the Falcon altar. As you can see, this altar, it looks like a falcon. And it was very important at that period of time for that society to attain precision and perfection in this construction, because they believed that only then the fruit of the ritual that is to be performed on this altar can be achieved if it is precise, perfect, to the point. And that, endeavor for attaining perfection led to these beautiful geometric results. And as you can see, there is a timeline, approximate. All of them are Bodhayan, Manava, Apastamba, and Kattayanam. These are 4 pioneers, Sulva Sutrakar. And these were translated into English first in 1875. So long back it was translated and it reached Europe by Thibaut. And then the great Vibhuti Bhushan Datta, the Bibi Datta, of Datta and Singh fame, that Vibhuti Bhushan Datta, who later became Swami Vidyaranya. In 1932, he did his own research. And then, comparatively recently, an American mathematician, Seidenberg, a historian of mathematics, Seidenberg, 1962 and 1978. And that's not the end. Still, people are working on it. As you can see, it's a book from 2016 only. A French historian of mathematics, Les Mathématiques de l'Hôtel Védique, le Bodha and Shulva Sutra et sa commentaire, Shulva Dipika. Shulva Dipika is one of the commentary on Shulva Sutra, and this is a book exclusively written on that. In 2018, Michel Danino is in IIT Gandhinagar, the Padma Shri, who has written a review of that book where he is pointing this out in a long discussion on the so-called Pythagoras Theorem, which Bodhayan expressed differently. That's important. Bodhayan expressed Pythagorean theorem in a different manner. That shows the indigenous aspect of it as the property of the diagonal of a rectangle rather than the hypotenuse of a right angle triangle. Pythagorean theorem, the usual version, it's in terms of a right angle triangle and its hypotenuse and other sides. Bodhayan expressed the same result, but in terms of the diagonal of a rectangle. So how exactly was it? So this is the Sanskrit sloka. Dirgha chatura sakshnaya rajju parshamani tirjangamani cha jat prithak hude kurutas tamu bhayam karati. Again, allow me to just break these Sanskrit words word by word. These are in Shandhi, they are conjoined. So that's why sometimes it appears to be difficult to understand. But if you just break them out in separate words, it becomes much, much easier to understand. So what does it tell actually? This is the Bodhayan Shulva 48. It says, if you just literally translate, Dirgha Chaturasra. Now Dirgha Chatura is a rectangle. Shrama Chaturasra is a square. Dirgha is one side larger than the other. That's the Dirgha Chatura, rectangle. So in our present day presentation, I have this picture in front of you, A, B, C, D, right? So don't think that Bodhayan have written this ABCD. This is what we have written to make things easier for us to understand and follow. So this is the rectangle. Akshanaya Rajju. So Rajju is the cord, the Shulba. Akshanaya Rajju means the cord along the diagonal. And then Parshamani, Parsha is side. So Parshamani and Tirjangmani, transverse side, Tirjak. So side and the transverse side, which we call length and breadth. Jat Prithagvute Kuruta. Now these two, Parshamani and Tirjagmani, whatever they do separately, Prithagvute. This AB and AD, they do separately something. What? That is not categorically stated here. Let us accept that. It is stated that the diagonal does that together, alone. Stamu bhayam karoti, ubhaya. Stamu bhayam karoti. This Akshana Rajju alone does that what the Parshamani and Tirjagmani, the length and the breadth, prithak bhute kuruta. What they separately do, the diagonal DB alone does that. Now that's the literal translation of the sutra. Now people who want to object to the fact that this is the Pythagorean theorem may tell, and do tell actually, where is it told that this area of the square has to be taken on these sides? It is not categorically mentioned. Two things are to be understood here. First of all, what is this idea of sutra? This is a Bodhayan Shulva Sutra. These are sutra literature. The idea of sutra is, it has to be very crisp. You know, this is the time of Indian civilization when everything was run by Shruti. The entire knowledge system was governed and maintained by Shruti, hearing and remembering. The idea of writing out things was not there in ancient India. You have to remember, you have to listen to it and remember. So that is why this has to be very crisp as possible. The definition of Sutra, if you look at the Vishnu Dharmottara Purana, it says, Alpaksharang Ashandigdham Sharabat Vishyato Mukham Astobha Manavaddam Cha Sutrang Sutra Vido Vidhu. See, the very first word of definition of what can be a Sutra is Alpaksharang. It has to be stated in small number of syllables. And Ashandigdham, you cannot, it cannot have 2-3 different meanings. You cannot question it. It has to have a unique meaning. Sharobat, it's like a gist. Shar. Vishyato Mukham, it must be universal. It has to be applied to every similar situation. That's the spirit of a theorem. Universality. Astobham, there should not be any meaningless term involved. There is no scope of poetic license, to make it sound beautiful, you add 2 more words. No, that's not allowed in a sutra. It has to be very crisp. So that's one aspect of a sutra. When you look at it and try to understand what is its meaning, you must understand that this is not a self-sufficient thing. This was to be remembered and it to be explained by the guru to his disciples. That was the Gurukula system. This is to be remembered. But this is only the crisp, the nutshell kind of thing. It has to be explained. Well, all this said and done, still you can ask, how do you know that the Guru explained to take the square on the sides? Who tells you that? Yeah, that's a good question. That's a pertinent question. And the answer to that is found in Bodhayan Shulva Sutra number 50. The same book, the very next results are application of these sutras. So let us look at one of this application, how this sutra is being applied. So let us look at this one. This is the Shulva Sutra number 50. What does it tell? Nana Choturasre Shamashan Kaniyasa Karanya Bursiasa Bridhram Ullikhed Bridhrasa Akshanaya Rajju Shamastayo Parshamani Bhavati. Okay, fine. Again, let us break it word by word and try to understand the inner meaning of this Sutra. Nana Choturasra. Choturasra, as I told you, is the square. Nana Choturasra means different squares. So now we are not talking about one single square. You are talking about two different squares. In our picture, the picture, I thank my good friend Amartya Kumar Datta of ISI Kolkata for lending me this slide. Originally, I have done something else on that too. But anyway, the original slide belongs to Amartya. Quite a few slides in the Silva Sutra. And I thank Amartya for that. This was in his lecture, Mathematical Gems from the Vedic Age. So with his consent, allow me to show you this beautiful picture here. In our modern day terms. So ABCD, please go with me. ABCD is one square. There is another square, ICGH, a smaller one. Two squares of different size. So what is the problem? The problem, Shamashan. The problem is to amalgamate these two squares and make a larger square whose area will be equal to the sum of the area of these two squares. I repeat, the problem is you have two different squares. You want to amalgamate them and make one larger square whose area will be equal to the sum of the two squares. And this is not to be done by mensuration, not to be done by algebraic formulae, by pure geometry. That is the challenge. The pure geometric idea, exact construction, ruler and compass construction kind of thing. Exact construction. It's not that you just calculate the area and sum it up and make the square root and tell that that is the length of the side. No, this is not that approach. It's a pure geometric approach. And how do they solve this problem? So that is here. Look here. Kaniyasa Karanya. So Kaniyasa is the smaller. Karanya means, Karani means to mark off, to cut off. So Varsyasa is the larger. Kaniyasa means smaller. So from the larger Bridhram, so the larger side, the smaller one is cut off or marked off. So what is larger? As for my picture that I have taken here, A, B, C, D. So this BC is the larger side. So from BC, I mark off CG. I hope you can follow. BC is the larger side, the one having larger side, and CG is the smaller one. So from BC, I mark off BE, which is equal to CG. So from larger one, I mark off the smaller one. That's the first part. Kaniyasa Karanya Barsyasa Bridhram. Ullikhed Bridhrasya. So this Bridhram means this augmented figure. Once you mark it off, see, one side was already AB. Now you have another side here, BE. That gives you an augmented figure. Ullikhed Bridhrasya. So this augmented figures, Akshanaya Rajju. Now that term is already known to you. Akshanaya Rajju means diagonal. So of this augmented figure, what is this augmented figure? It is now a rectangle, ABEF. Its Akshanaya Rajju, Shamastayo Parshamani Bhavati. This Akshanaya Rajju, this diagonal becomes the necessary side, Parshamani, Shamastayo. Shamasto in the sense of amalgamated. The amalgamated figure that you want, its side, the Parshamani, Bhavati, it becomes the side of that required amalgamated figure. Now, can you see a Pythagorean theorem here? Can you see the application of the previous rule? It tells you that you have a square with side AB, you have a square with side CG, and according to your construction, CG is equal to BE. And now you have this rectangle, and you say that the diagonal AE is the required side. Required for what? To have the sum of the squares. Having one single square whose area is the sum of the squares. And that tells you AE square is equal to AB square plus BE square. Pythagorean theorem or not? Now you ask yourself. Now you ask yourself. That's it. And this is not the only example that we can give. Let me give you another one. This is from Katyayana Silva Sutra. Look at the beautiful construction. What is this construction for? What is this problem? The problem is to draw a square n times a square of a given side. So again, the problem is you have a square of a certain side. For our understanding and communication ease, I take the side to be A units, the way we deal it today. So you have certain number of squares of side length A. Certain number, unknown number. You don't know the number, my friend. Now look at this sutra. It tells you how to find out that square whose area will be the sum of all these squares of equal size. Well, if you apply mensuration, if you apply your modern idea of algebraic computation, it is simple. You have some n number of squares, perhaps, each having a square as its area. Then total area will be n a square, and you want one single square whose area is n a square, so its side has to be root n into a. Very simple. But again, these people, these geometers, these Sulva Sutrakara, they are not going by this formulae. They are going by pure geometric exact construction. No approximation. Exact construction of this value of root n into a. In their language. Of course, there was no n, there was no a. It was stated in language, in Sanskrit, as you can see there. Yavat pramanani shamochoturasranne ki kartung chikirsha dekonani tani bhavanti tirjaka digunanne katekadhikani trayastrir bhavati tashyeshu stat karuti. Allow me to break it up again, term by term. I hope you can follow. So first word, Javat pramanani shamochoturasranne. Javat, you know, Javat and Javat Tavat is a standard word used for unknown number of things. Just like in algebra, you use x today. Something is not known, so you say, suppose there are x number of things or n number of things. So this Javat was the idea of something unknown. Pramanani Shamachaturasra. Shamachatura, you know already, it's a square. Pramanani, in the sense, every square now taken under consideration are of a certain fixed side. Pramanani, Shamachaturasra. Eki kartung. Eki kartung is amalgamation. So what you are trying? You are trying to amalgamate certain number of squares of given equal side. You want to amalgamate and make one single square out of them, geometrically. You would like to know what will be the length of the side. That's the problem. Shamachaturasranne eki kartung. Then the rest of the thing is to give you the method for construction. So let us look into the method. Chikirsha dekonani tani bhavanti tirjaka. Chikirsha. Chikirsha means desire. What you want to find. Chikirshat ek unani. Una means less. So ek una means one less. One less than the desired number. Tani bhavanti tirjaka. Tirjaka is the transverse side. So transverse side of what? That I will tell you. But first try to understand Chikirsha dekonani. That is n minus 1. N is the desired number, that is given number of squares. You take one less than that. That's the formulation. That's the formula for your computation that is being given here in language. N minus 1 into the given length. Tani bhavanti tirjaka. Tirjaka means a transverse side. Side of what? If you just jump 2-3 words, you find this word traya. Traya srir bhavati. Can you see this? Traya means the tribhuja, the triangle. So this is going to be a triangle construction. It refers to a triangle, traya. What kind of traya? Srika. Srir bhavati. So this srika means the arrowhead. So this triangle is like an arrowhead. So what is an arrowhead? It's an isosceles triangle. It's an isosceles triangle, so of which the tirjaka, the unequal side, is this n minus 1 into a. Now it is clear. Chikirsha dekonani tani bhavanti tirjaka. Clear? So unequal side, the so-called base of this isosceles triangle, is n minus 1 into a. What about the other information? Digunanne kata ekadhikani. Diguna, digun means twice. Ekata means together. Ek adhikani. Previously it was ek unani. Ek una. Una means less, so it was n minus 1 into a. Now it is ek adhikani. One more. It is n plus 1 into a. But this n plus 1 into a is actually twice the sum of the two sides. It's digunannekata. So each side of the equal two sides of the isosceles triangle is n plus 1 into a by 2. It's diguna. So it has to be halved if you want to get hold of one side. And together it is twice, ekata. So digunannekata ekadikani. It leads to the fact that the base is n minus 1 into a. The equal sides are n plus 1 into a by 2. So now this srika is made. The arrowhead is made that way of this arrowhead. Now this arrowhead, how do you differentiate one arrowhead from the other? All of them are isosceles triangle. They are differentiated by their height. So this height, tasheshus tatkaroti, the height of that will be the required length. And what is this height? Now apply your knowledge of present day algebra. They are not telling you how did they get hold of this result. That's one very unfortunate aspect of the entire ancient Indian school of mathematics. They never tell you how did they get hold of things. They just tell you what is what. And you know, this continued till Ramanujan. Just like he told you, this will be the fact. Now it is your job. If you don't believe me, go and check and find it out for yourself. I know it will be the truth. And years after years, we are getting to know, yes, those are really, really, really truth. But they never tell you, how did they get it? Perhaps Ramanujan got the idea of this presentation of mathematics from this ancient Indian tradition and style. Just like here. They don't tell you how did they come to know it, but your present day idea, the translation of their problem to our present day language as I have tried, will tell you that this height is nothing but, according to Pythagorean idea, the theorem that they already know, that I have already established. It's a right angle triangle now, right? If you drop that perpendicular in the isosceles triangle. So this is root n into a, because this is n, after all, this is equivalent to the algebraic formula that n plus 1 into a by 2 whole square minus n minus 1 into a by 2 whole square is n a square. So the length is root n into a. And you see, most importantly, mathematically, it is exact construction. It is exact construction of root n into a. The irrationality is not becoming an impediment. It would have been an impediment if you want to construct it algebraically, numerically. Then you won't get exact value of that if you want to have the exact value in the decimal system. You all know that. But look at the advantage of this geometric approach. You get the exact length. And that length, if you take the side as that much, then that is the required side of the square whose area is the sum of all these squares. Isn't it beautiful? Isn't it geometry? And these are done much earlier of Greek geometry. And we are said, we are being told that geometry comes from Greece. There's no geometry in ancient India. You learn yourself and then make your own judgment. I'm not going to tell you what should you decide. It's up to you. It's an open forum, always. Academics should be like that. Don't depend on my interpretation of it. If you are interested, read more. There is no dearth of such, available references. Read the books. Original books, secondary translations by experts, and frame your own opinion. Last one in this genre today that I can discuss, I have a plan to discuss, is this one. One of the most fantastic construction. And why I am discussing this particular one? Because they are all somehow or other related to the idea of Pythagorean theorem. This one is to construct a square equal in area to a given rectangle. I think everyone has done that in their school days. It's a very common question in 10th standard. Geometry, construction, that construct a square equal in area to a circle. It is there in Pythagorean, in Euclidean doctrine. Standard, a very common question in the final exam. And look what Bodhayan has to say here. This is rule number 54 in the same text, Bodhayan Shulva Sutra. 48, then 50, and then this one is 54. It says how to construct a square equal in area to a given rectangle. Dirgha chaturasra, shama chaturasrang, Chikirshang, Tirjangmani, etc., etc. So now these terms are already very well known to you. It should be. Last half an hour I have been talking about these terms again and again. Dirgha Chaturasra. So now you know the meaning. It's a rectangle. Shamo Chaturasra. It's a square. Chikirshang. So that's the desire. So what is your desire? What is that you want to do here? You want to make a Shamo Chaturasra from a given Dirgha Chaturasra. That's a problem. Area must be same. You are given a rectangle. You want to convert it into a square of equal area. And what is to be done? That's the rest of the sutra. Stirjangamaning karaning kritva. So the word karani, that is already known to you. Karani is to mark off, to cut off. What is to be cut off? Stirjangamani. So stirjangamani is something already known. We have already described that word. Stirjangamani is the transverse side. That means the breadth. So the length is the larger one, usually AB. So again, come to this beautiful picture drawn by Amartya. This is ABCD in our present day term. AB is the length, CD is the breadth. Clear? So for easy reference, suppose the length is A unit, the breadth is B unit. So in our modern day mensuration language, it is AB, the area, square units. And that has to be the area of the square as well. So the length of the side of the square ultimately will be square root of AB. But again, it's not a mensuration problem. It's a geometry problem. So they are going to do it by exact geometric construction. How? Stirjangamaning karaning kritva. So from AB, you cut off the length of the other side. That's the stirjangmani, the breadth. B. The smaller side is marked off. So as you can see here, if you just kindly follow me here, AB, the length is a small a unit. And from that you mark off this AE, which is small b unit. Then karaning kritva, after that what do? Shesham didha vibhajya. Shesham is the remaining part. EB, the remaining part, the remainder. Didha vibhajya. Divide it in two equal hubs. Dedha. Two equal hubs. So what do? The remaining part is what? A minus b. A is the whole length. Small b is up to AE. So this is the midpoint of that, G. So this EG is now A minus B by 2 in length. In our language, this is to appreciate what is being said, right? So this length for us to understand is this A minus B by 2, EG. Karaning kritva shesham didha vibhajya. Then viparjashe tarachya padadhyat. So just break it up. Viparjashe itarat cha upodadhyat. This is being, made sandhi. Viparjasya means now you reverse your direction and proceed in that direction. Viparjasya. So after you get this midpoint G, don't go to that B anymore. Now look back. Reverse your direction. So you just look back here. And itarat cha upodadhyat. So you just add them. Reverse your direction and move in this direction and add these two. So what do you get? What do you get? This much was B. This much was A minus B by 2. So viparjashe tarachya padadhyat. What you get is B plus A minus B by 2. That is actually A plus B by 2. So that's the length A plus B by 2. That's what you have now. And then khandam abhapena tat sampurayet. But this length somehow is this started with B, right? Tirjangamani. That is khandam abhapena tat sampurayet. So it is deficient. There is a difference and that has to be completed. Tat sampurayet. This B that with which you have started is deficient. Deficient from what you need. What do you need? In our language, I need root AB. Now they say it is less, this B is less. But you can achieve that. Where? You see this E at this point E, if you draw this line here and take this radius A plus B by 2, you see this arc is drawn and now you see how this B, which is EF, is less. And you have to extend that. Tot sampurayet. You have to complete that. Extend. It is khandam. It is less. It is deficient. There is a abhapa. And you have to complete it. Why? Tasya nirharaha utkaha. Utkaha means also desired length. To get hold, nirharan, to get hold of something. To get hold of the desired length, you have to complete this deficient part. That means EF has to be extended to this point. And this is the required length. Tasya nirharaha utkaha. Again, look at the mathematics playing behind. This again turns out to be a right angle triangle, of which EG is the base, which is a minus b by 2. The so-called hypotenuse, that is the radius of this arc, which is a plus b by 2. And now you know a plus b by 2 whole square minus a minus b by 2 whole square is ab. So this is root ab whole square. So that's the length root ab you are trying to find. Tasya nirharaha utkaha. And look at what Seidenberg has to say in his book Origin of Mathematics in 1978. This American historian of mathematics is writing, this is entirely in the spirit of the elements of Euclid, book 2. Indeed, I would say it's more than the spirit of book 2 than book 2 itself. And you say that geometry was developed first by the Greeks. Ponder upon it. Think over. This is an exact construction. I just have another quote from Seidenberg. This is another Origin of Mathematics, the book I have referred to, 1978. He says that nor did he means Thibaut here, the gentleman 1875 who did the translation of this in English, nor did he formulate the obvious conclusion, namely that the Greeks were not the inventors of plane geometry. Rather, it was the Indians. At least this was the message that the Greek scholars saw in Thibaut's paper, and they didn't like it. If the Indians invented plane geometry, what was to become of Greek genius or of the Greek miracle? You know, there is a school of thought. It's called Eurocentrism. This school of thought, this philosophically, it begins with a kind of axiom that ancient Greece is the cradle of our modern day science or modern day civilization. Everything has to be there in the ancient Greece. And that's what this gentleman Seidenberg is pointing out. If the Indians invented plane geometry, what was to become of Greek genius or the Greek miracle? And most of the refutations were merely authi dismissal. If you have to refute that these statements are wrong, you have to justify why you should think that this Bodhayan and company should not be given credit for early geometry. You have to explain that. That has never been done. Simply a kind of highbrow attitude, authi dismissals. Anyway, damage had been done, and the Sulva Sutras have never taken the position in the history of mathematics that they deserved. I just give one example of such an authi dismissal as I see it from Professor Amartya Sen, the learned Bharat Ratna. You see, one must understand, and I must clear my position here, that I have the highest of respect and esteem from this for this luminary of our time. It's one of my proudest moments of my life that the translation of Ramanujan's book that Ambar has pointed out in Bengali, it was formally released by Professor Sen. So I have nothing against him personally. I have the highest of respect, and I don't consider myself even an iota of his scholarship. But still, most humbly, I beg to differ with his views here. What he says in his book, The Argumentative Indian, as it happens, despite the richness of Vedas in many other respects, there is no sophisticated mathematics in them. Vedas does not mean the Samhitas only. It's the whole genre, Vedic genre. These are in Jajurveda. This Sulva Sutra, they are Jajurvedic recensions. They are related to that. Jajurveda is the Veda in which you find this ritualistic performance and the rules of that, and this is related to that part. And he says there is no sophisticated mathematics in them, nor anything that can be called rigorous science. I had the audacity of writing letters to him, mail to him, most humbly asking his opinion about this Sulva Sutra and its interpretation and its time frame, that why did he consider that there is no sophisticated mathematics at that point of time. But unfortunately, I didn't get any response. Maybe I'm too small a fry to be responded to, but it stands there that what I understand of it, I find this view of most learned Professor Shen something unacceptable. And here he says there was, however, much of both in India in first millennium CE. Yes, because this suits that Euro-centric view, that everything in India came from the Greece, the Greek invasion of Alexander, and with him came the Greek science to India, and India became educated in modern mathematics and science. That's one way of looking at the fact. That's called Euro-centric view. But in that view, this time frame and the mathematics of Shulva Sutra, Pingala Chanda Sutra, these things do not fit in this doctrine of Greek supremacy. The point is, academicians must then clear their stand. Either they should try to interpret that these sutras are all wrong, these are not the correct interpretation, or they should try to establish that these sutras are much later. The time frame that is given for them is wrong. It was actually done later, after Alexander came and all these things. But you just cannot ignore them. Unfortunately, that is being done. That is being done by a good school of scholars. They just take an eyebrow, a kind of highbrow attitude. Once you say that Pythagorean theorem was there, they'll say, oh, come on, this is rubbish. These are all political mumbo-jumbo. Well, there may be many political mumbo-jumbos. We see that, and we detest that. But this one is not a political mumbo-jumbo. It is there. You cannot put them on the same footing. That's my point. You see, J.B. Narlikar, Jayant Vishnu Narlikar, in 2003, he writes, Shulva Sutra contains, for example, Pythagoras Theorem, but not the proof of the theorem. That's another very important aspect of the whole thing, whole discussion. There is no proof, as Euclid's element does. Nevertheless, as a correct result, the statement should be renamed as a Shulva theorem. That's what he feels. But what Manjul feels is, several verses in Shulva Sutra make it pretty clear that Shulva authors knew why the theorem is true. See, you must understand, Shulva Sutra was a kind of manual. It was not a geometry book. These years, first of all, that was a Shruti period. And this idea of proof that is accepted today in mathematics is definitely of Greek origin. This deductive argument of starting with something and step-by-step deduction to reach the conclusion what we accept as a valid body of a proof in mathematics is definitely Greek in nature. The Indian idea of justifying some claim was not the same. That doesn't mean that there was no proof of it. You can't search a proof of Indian genre in a Greek text. Neither you can do the reverse. There was a different way of justifying things in India. It's called Upapatti and others. You have to get into that. But you cannot say that since the proof is not there, proof, quote unquote, per se, as the Greek elements does. So I will say that they didn't know the proof of it. It was empirical. No. If it was empirical, then they could not have allowed themselves to use it again and again for such general enunciations. You have seen two, three such examples already. Those are absolutely general enunciation. Those are not dependent on a particular number. This is not a kind of, particular triplet that I find and say, oh, these three numbers I write and see that a square plus b square happens to be equal to c square. And I don't know nothing about the general thing. Only these three numbers I know. That's called empirical evidence, as was in Babylon. As you can see in the Babylonian clay tablets, a list of so-called triplets, which are Pythagorean in nature. You can say that these are empirical. But when you are applying this, as you have seen in Shulva Sutra, they are applying the result to general cases. You have seen that. This is very much theorem-like thing, applicable to any length, any n and any a. You can calculate what is root n into a by that formula. You can calculate for any a and any b, any rectangle, how to convert it into a square and equal area. It doesn't depend on particular value of a and b. It's not an empirical idea. It's absolutely like a theorem. And that's what Seidenberg also pointed out in his book in 1962, The Ritual Origin of Geometry. Many writers who refer to Shulva Sutra say there are no proofs there. We can only suppose that these writers have not bothered to examine the work. Get into the deep. Examine the work and you will feel that these people knew the proof. Perhaps that was discussed in the Gurukula. That was discussed face to face. From the Guru to the Shishya. Not to be, recited and remembered. If you have to judge a society, you have to judge the society the way it was. And it is a known fact that there was no writing at that point of time. These Shulva Sutrakar, they were not writing a geometry text as Euclid did. They had no intention of telling you how did they achieve this result. Doesn't mean that they didn't knew it. It's not as simple as that. And this is what my notes is. Shulva Sutras are meant to be engineering manuals, not expository texts. They are offshoots of much older Vedic tradition, which had savants who had not only realized some of the fundamental principles of plane geometry, but knew why they worked and how they yield accurate construction. That's about Shulva Sutra. Similarly, Chanda Sutra, Prasadi by Pingala. Chanda was one of the important Vedanga, one of the 6 limbs. There are 310 odd, some says 312 sutras in the 8 chapters divided. And the 8th chapter, this one great fact is somehow this book is extant. It was written at a much later point of time, of course, but that original text, along with quite a few works done on that. There's a list of this. This is with due acknowledgement to Jayant Shah, who has written a fantastic paper on this Chanda Sutra by Pingala. This is 2nd or 3rd century BC. Then you have the Natya Shastra of Bharata, where ample reference to Pingala's work is found. And the most important one is this Mrit Sanjivani by Halayudha in 950, Vrittaratnakar by Kedarabhatta, and this fantastic book by Virahanka, Vrittojati Shamuchaya, 7th century, and this is in Prakrit. It's not in Sanskrit, this is in Prakrit. And here in Virahanka's work, with reference to Pingala, we find clear reference to what is now known as Fibonacci sequence. Even if you go back to Pingala himself, there is a seed of that. You go into details, I can talk about prosody of Pingala Chanda Sutra for hours. I've written a book on that, but unfortunately that's in Bengali, so I can't refer you to that. But there are other, English, papers and research works, articles by many scholars. So if you're interested, you can read that in details. In Bengali, there was none, so I thought of writing one in Bengali recently in this particular year, taking the advantage of this additional time that my good friend Ambat has pointed out. I have completed that book and it is available in net as well in e-commerce, but that's in Bengali. So 7th century Virahanka, and that is 13th century Fibonacci, and with a complete different frame of reference. Fibonacci did it, you might be knowing that, in breeding of something, what it was, rabbit breeding. Virahanka got it from the prosodical analysis. And not only this Fibonacci sequence, these are the basic questions addressed by Pingala in his 8th chapter. If I have to get into that in details, like I tried with 2-3 Shulva Sutras, it will take me two more hours. I don't have that time. So I'll just tell you the problems and encourage you to read it in details. In the works done by others, I'll give you some references at the end. So these are the questions, general questions of general nature addressed by Pingala. If you are thinking, what is there to do with, prosody analysis and mathematics? Prosody, in the Indian context of Sanskrit prosody, everything is divided in 2 different kinds of sound morphemes. This is called Laghu and Guru. They're called Akshara, syllables. Akshara, Laghu and Guru. So in English, you can write L and G for that. So one way is to count the appearance of these aksharas in a particular meter. And accordingly, the meter is named. It's given a particular name. So this is basically, as you can see in spirit, this is a combinatorial thing. How many ways these laghus and gurus can be assigned to certain available vacant places so that a new kind of rhythm, a pattern, which is given a particular name of a meter, like Gayatri meter, Jagati meter. So many of them. I'm not going to, name unnecessarily, because that's a completely different aspect. The idea is how many ways you can put this laghu and guru. The places are vacant. That's the kind of, sum that you deal with in your class, maybe 11th standard, or 12th standard, that there are n number of places vacant. Each place can be filled in by laghu or guru and repetition is allowed. How many ways all the places can be filled? In no time you will say it's 2 to the power n. But there is a beautiful algorithm reaching to that goal in this 8th chapter of Pingala. And that algorithm, there's 4 sutras designing that algorithm. 2 of them refer to Shunya, 0. There are the 4 sutras, Dhirardhe, Rupe Shunyam, Di Shunne, and Tabat Ardhe Tad Gunitam. These 4 together leads you to that algorithm that answers 2 to the power n as the answer to this particular question. And in explaining that, it leads to a fantastic algorithm. That itself is another important point, my friends. The word algorithm, as it stands now, it comes from the name of Al-Khwarizmi. That was Latinized. Al-Khwarizmi was a court mathematician in Caliph Al-Mamun's court at Baghdad in 9th century, where works of Brahmagupta from India reached some 100 years back. One mathematician called Al-Fazari translated that in the name of Ziz al-Sindh Hind. Young Al-Khwarizmi worked on that book, translated it, did some original work, and later has written this book, Al-Jabar wal Muqabala. This word Al-Jabar later was translated into Latin, and that actually is the origin of the word algebra. And also this name of Al-Khwarizmi was Latinized as algorithmi, and later on the English word algorithm, which means initially, which used to mean doing mathematics in the way of the Arabs, in the ways of the Al-Khwarizmi book. And later on, the word algorithm has a standard connotation meaning now. But the origin is that 9th century Arab gentleman, Al-Khwarizmi. And my friend, here I am talking about 2nd or 3rd century BC, more than 1,000 years back in India, a categorical example of algorithm, telling you how to reach this goal of 2 to the power n. These are the 4 basic questions that was addressed and answered by Pingala. Each led to fantastic mathematics. I'm afraid I can't sit on that. I can explain all of them in this short time because I have some intention to tell something else as well. I just give you this list, contrary to what I started with. You can see decimal to binary conversion, which is usually ascribed to Leibniz, and binary to decimal conversion. You can see the so-called Pascal triangle in it. In the 8th chapter, one of the sutras that lead to the formation of these binomial coefficients, their sum is usually ascribed to Newton, and the clear reference to mathematical zero as Shunya. All is there. But you need to study that. And today, this is not the right time, so I'll skip on that. I'll give you reference of English books or articles which you can go through. One paper I have already mentioned, that very good paper by Jayant Shah. The original initial paper was written by one Dutch historian, Van Newton. Binary arithmetic in ancient India, binary arithmetic in Pingala Chanda Sutra. You can read this and try to appreciate and understand this. This is the Bengali book. If some of you, I was checking some of the names that was flashing on my screen before I started talking. Quite a few are Bengali names. So if you are interested, you can get hold of this book and try to understand. I've tried my level best to explain things as lucidly as I can, the idea of mathematics in Pingala Chanda Sutra. And just refer to this fantastic sutra of Virahanka in 7th century AD. Now this is on Matra Britta. So chandas, these are Abritta chandas that repeats itself again and again. That's called Abritta. Now there are Akshara Chanda and Matra Chanda. Akshara, as I told you, Akshara is syllable, Laghu and Guru. Matra is another way of assessing these chandas. This is in terms of the time required to pronounce that. Usually, 1 unit of time is ascribed to Laghu and 2 units of time is ascribed to Guru. That leads to the Matra Britta. The other one is called Varna Britta, Varna, that is Akshara. That's the usual one. And now in this text, Virahanka is Britta Jati Shamuchaya. He is telling, Ebangcha Varna Vitte Matra Brittana Mannatha Bhavati. So he is just analyzing certain particular aspect of it, and he is claiming that the Varna Britta was something that I have already described. Matra Britta is a different ballgame. Annatha Bhavati. It happens a different way. How? And that is the explanation in the next line. Do purbo vikalpo ya miloita jayate shankha. Now this shankha does not mean number. This shankha is a jargon here, which refers to that 2 to the power n. That kind of thing. And what he says, do purbo vikalpo. Purbo vikalpo. The one immediately preceding and the one even before that. These two, miloita, is to be added, gives you that number. Sa uttar matranang shankhaya esha nirdesha. The next one, the next tire, the matra meter number that you are trying to compute. How many different matra meters can be made? The next tire is actually the sum of the previous 2 tires. Sn is equal to Sn minus 1 plus Sn minus 2. The generating rule for the famous Fibonacci sequence. Do purbo vikalpo ya miloita jayate shankha. Sa uttar matranang shankhaya esa nirdesha. Not only in Virahanka, another later text, still before Fibonacci, Hemachandra, we find reference to this rule. Ankanto panta jogaha pare pare matranam. So you see that matra being referred, the matra chanda analysis. Ankanto panta jogaha. So anka, anta and upanta, last and the last but one, jogaha, adding them. So add the last one, the previous one, and last but one, even before that, add them. And the next matra, pare pare matranam, you get out of the sum of these two. The same rule. So that was explained by Virahanka in 7th century and Hemchandra in his text 1150. And we say it is Fibonacci sequence. You decide. I come to Bhakshwali Manuscript. A little bit time that I have left. Now this Bhakshwali Manuscript is the oldest written text extant for India that we have. It's the oldest one. The exact time frame of Bhakshwali Manuscript is again hotly debated. You know, this is found in 1881 at a place 80 kilometers northwest of Peshawar. This is completely mutilated. It's found by one cultivator He was trying to actually level the land of cultivation and digged it up. And because he was not very, conversant with learning and all this process, maybe in his hand itself, it was further mutilated. And then ultimately it reached, this is the time of British India, as you can see, 1881. Calcutta was the center, so it reached Calcutta Madrasa. There's one gentleman, Hornell, who was an expert of ancient languages, ancient Indic languages. So he was the first one to decipher this script. It's written on a birch bark. There are 70 incomplete leaves. It's written in the Gatha dialect of a Prakrit in Sharda script that was prevalent at that Kashmir region at that point of time. It's a very interesting fact about Bhakshwali Manuscript, its age. See, it was later sent to Oxford, Bodleian Library, and it is still there. As you can see that it is, every single page is cased in this kind of book, in the mica sheet. This is completely, absolutely fragile. You just cannot take it out. And you have to take photographs of that and what have been done on these photographs. And a very interesting thing happened 3 years back, when Oxford people, the Bodleian people, they have done a radiocarbon dating of 3 pages of this arbitrarily, page 16, 17, and 33. So these page numbers are also not given by the original Bhakshwali writer. Nobody knows. This was arranged by these experts in terms of the content of the pages. So in that sense, the very interesting finding is the 3 pages, as you can see in front of you, they came out of absolutely different ages. 3rd century, 7th century, and 9th or 10th century. And then hot debates are on. How come 3 different pages of the same manuscript can be of such a huge different time frame? I personally think that if you go through the Bhakshwali text, there is a colophon that tells that this is written by one Chajaka Putra, who claims himself to be a prince of calculator, and he is writing it for the use of one particular family. So it was a kind of family treasure. A family perhaps was a family of, businessmen who were doing business and this kind of arithmetic. This book is replete of arithmetical sum. Fantastic, fantastic problems. And another tremendous significance of Bhakshwali is the fact that here you have written zeros. That's why the timing, the dating is absolutely important. This clears out what is the time, at least, when India have started writing zeros. And it is fantastic fact to know that those zeros are not the modern looking zeros that you are accustomed with. These zeros are like bold dots. These are called bold dot zero. Initially, India used to write it that way. Much later, there's the oldest one we know is from 9th century. In stone inscription is there in one of the shrines in Madhya Pradesh. There is a Gwalior fort. There's a Chaturvuja temple there. And there is one particular writing on the, it's inscribed on stone inscription by King Mir Voja. And there you find that numeral 270 inscribed. And that zero looks like our modern day zero. That's the oldest known stone inscribed zero. There are other similar looking, modern looking zeros of earlier date, but those are on copper plates. And their authenticity is hotly and bitterly debated among the experts. Some experts claim them to be original, acceptable, and some experts, of course, from Euro-centric point of view, they say that these are latter forgeries to establish Indian priority and supremacy. These were forged, but not with, not with substantive argument or proof. But this is the state of the affair. So Bhakshwali manuscript, the zeros, as you can see here in front of you, this is one of the pages of the Bhakshwali, and these large numbers are written over there. And these are all zeros. I'm showing you. These are all zeros, Bhakshwali zeros. So what kind of mathematics was there in Bhakshwali? This is an arithmetic text. So I will just tell you about one particular amazing formula that is there in Bhakshali. So this is the idea of numbers. This is the numerals 1, 2, 3, 4, etc. And this is the 0. As you can see, this is the Bhakshali 0. And this is one page of the Bhakshali. This is page 46. R in the sense of recto. There's two sides, recto and verso, the front side and the back side. So 46R, there you find these numbers, and these numbers, if you transcribe, these are the numerals. All of them are these numerals. This has been researched upon right from the time of Vibhutibhushan Datta to the present modern Taka Hayashi and many other scholars. They worked on that, deciphered them, tried to complete what is missing. You see, these are all, it's not the complete manuscript page, as you can see. Mutilated, a certain part of it has gone forever. But the rest of the calculation, since you can follow from the previous page, you can complete the rest of the calculation. And it matches with the existing one. And that's how you can see here 3 colors are used here. This is one from Bill Castleman. Thanks to him for this beautiful, presentation of this page of Bhakshali. The colored yellow things are what you can see actually on the Bhakshali manuscript. The colored greens are almost visible, but not exactly. And the colored reds have gone for good. But if you calculate the whole thing, you can actually decipher and find out the total number, and you find that this has to be this number because the rest of the part matches your calculation. What is this calculation all about, this particular page? So this, and you see these are all fractions. Right now in front of you, what you see, these are Bhakshali fractions, decimal fractions, numerator and denominator. Interestingly, they didn't used to give that line, that horizontal line that we use today. When you write 3/5, you give a horizontal line in the middle, right? But in Bhakshali, you don't find that line. There are only these 2 numbers, numerator and denominator, one below the other written. And these such large numbers were there. They are doing huge arithmetic computation. What kind of computation? Computation about what? So I'll explain one such. This is an explanation of approximate square root finding. This is one of the sum. 6 such sums are done in Bhakshali manuscript. Finding approximate square. This is the Sanskrit rule for that. Akrite shlishta krityuna sheshacheda dishanguna tadvarga dalashang slishta iti shuddhi kritikhaya. Let me try to explain the meaning of it, get into the mathematical details in our present day language, and try to show you what this stands for. It tells you that you have a number which is akrite. Akrita means which is not a perfect square. If it's a perfect square, then its square root is fine. You can find that. But if it's not a perfect square, how can you find the approximate square root of it? That is the problem. Why were they hitting this problem? Because they were solving something more important. That was kind of arithmetic progression sums. Number of terms were unknown, and they were ultimately leading to something which is a quadratic kind of equation, and you have to find the solution, numerical solution of that. And that is where they needed this approximate square root calculation. And this is the rule for that. Akrite, slishto krityuna, sheshachhedo dishanguna. So in our language today, if we just try to explain what is told there. So Q is the number which is not a perfect square. So what you do is you take out the largest square part of it, and the rest is your residue. Like here, Q is a square plus R. So R is the part that is, debarring from making it a perfect square. That's the additional part, extra part. And what you do, what is the first approximation of the square root? The rule says this A square will lead to A, and this shesha, the remainder, it has to be divided. Shesha cheda, di shanguna, di twice. So twice of the first approximation, you have to divide this remainder by that. So the first approximation, the formula tells you, and once again, that frustrating fact that they don't tell you anywhere, that how did they get hold of this? We can calculate it. Now, I'll show you that yes, it happens to be the first approximation, a very easy algebraic way. But what was their way of reaching this result? It remains unknown to us. But the result is clear. Why? Because they have done 6 problems, 6 sums by this result, and step by step derivation of those sums actually match these results. So the first approximation is a plus r by 2a. Shesha cheda dishanguna. So the shesha, the remainder, is to be cheda divided by twice the first approximation. That's the approximation a plus r by twice a. That's the first part. Then tod burger. So make it square. This r by 2a. You make the square of it. And dala. Dala means to divide by 2. Dalan. So tad burger dala shanslishta. So this is the Shanslishta Karan, divided by twice the first approximation. That's the Shanslishta Karan. 2 into a plus r by 2a. See, the first approximation was a, then the correction, r by 2a, that's the first part. Then a plus r by 2a is already what you have, but that's not good enough. You go for the second part of approximation, and there it says that you square this first correction, r by 2a whole square, divided by twice of that first approximation. That sounds Slishta. And then iti shuddhi. Shuddhi is the correction. Kritikkaya. This correction is to be made. So it is to be subtracted. And look at this word, kritikkaya. Kriti is the square. If you ignore the square of the error, then you get this. That's the meaning of it. Word by word meaning of it. I'll try to explain. Mathematically, how do you reach this? A plus r by 2a minus r by 2a whole square by twice a plus r by 2a in our language today. An application of that, you can do it. Take your calculator, find out square root of 10, and you get this number. And apply this Bhakshwali rule. 3 square plus 1, a square plus r. Then according to this rule, 3 plus 1 by twice a. So twice into 3, 3 plus 1 by 6. Minus, this is r by 2a whole square. So that's 1 by 6 whole square minus twice 3 plus 1 by 6. Simplify. Reach the same result. Amazing. And it's more than amazing, my friend. I'll show you that this is the very same result of what you know as Newton-Raphson method. What Newton and Raphson reached by calculus. The same result. We don't know how did they reach it, but the very same result was reached by the Bhakshwali people. I'll show you. First of all, in pure algebraic terms, Q is a square plus R. I hope you are following me. That's the most, frustrating aspect of this E version of lecture, that I can't see your face. I don't know whether you are following me. I don't know whether I am being able to draw your attention. But then, okay, I have to accept that perhaps you are listening to me. And if you are, then here is enough thing to amaze you. See, you take a common, this is a plus r by a. Then you do this very simple calculation. Make it 2r by 2a, and this is r by 2a minus r by 2a, and r by 2a plus r by 2a. And that leads to this, a plus b into a minus b. And then it is a plus r by 2a whole square. Right? So square root of q, if you neglect this part, kritikkaya, you see? Neglecting the square, kritikkaya. Khoi is subtraction in Bhakshwali language. So you neglect this square, and what you get is this a plus r by 2a. That was your first correction. A was the first approximation, a plus r by 2a. And then, of course, this is not the exact value, so there is an error. So in our language, if you start like this, that's q, the square root of q is this plus some error e, then what you do is very simple arithmetic. Take the square of both the sides, simplify it, and reach this expression where you have e square plus twice e into this is this expression. So what is this e? Well, if you ignore e square, so once again you see, iti shuddhi kritikkaya, you have to ignore this square of the error. Just like here you ignore the square of the error, r by 2a whole square. Here also this ignore the square of the error. And what you have as error is this, minus r by 2a whole square into this. So that is to be appended here. That's the first correction, and this is the shuddhi, the second correction. And that's how algebraically you can reach today. I repeat that we don't know how did the Bhakshwali people, how did the Bhakshwali mathematician reach this goal. And this is the application of that you find in Bhakshwali. This is the kind of rational approximation to the solution of this equation. This arising out of analysis of a progression. 3 4x square. Of course, x was not there in Bhakshali. This is in our language. This is all stated in language. It was a word problem. Translated in modern day language, it looks like this equation: 3 4x square plus 3 4x equal to 7,000, and you are trying to find the x for that. And if you do that, then this is the square root you encounter with. And this calculation we find in details in Bhakshali. That is that particular page I have shown you already. This is the square root calculation of that particular page. This is the number 336009, and you are finding the square root. And there they are applying this formula. According to their technique, the whole square part, you take it out, that's the remainder, 768, and then you calculate these numbers. R by 2a, the first correction, and then the second correction, and then the refined root of it. And this is this large number, these large fractions that you get. 4, 5, 0, 5, 7, 6, 2, 6, and so on, divided by this number. And if you do this by your computer, by your calculator, you will be astonished to see that this is correct up to 13 decimal places. This is correct up to 13 decimal places. And that is not the end of the road. After finding out the solutions of these approximate solutions or every other solution in Bhakshali, they used to do something which was a kind of verification of the result. That is one of the idea of Indian proof. After doing this, after applying the rule and calculating and getting the answer, they used to put it back in the original equation, and adjusting the approximations, they used to check whether this equation is satisfied by the answer. And this adjustment of approximation is a huge and difficult calculation. And that calculation led to this kind of numbers, this kind of fractions. There was no decimal point. That if you just remember some of these digits, 507533 and ending with so many zeros, that is that particular page. Can you see it there? 50 here, 5075. Can you see that? Ending with so many zeros here. This is the number 50753383. I repeat here. This is 5 there. 507533. And that ends with so many zeros, right? That ends with so many zeros here in the denominator. 1, 2, 3, 4, 5, 6. And this is the denominator here. Denominator with 1, 2, 3, 4 zeros are visible. 2 has gone missing forever. But all the other digits, they match with this number. So the historians, the researchers, they're pretty sure that this exact number was actually this one. That's how this was actually calculated, researched, and revived. The whole Bhakshali mathematics. And I tell you that what is Newton-Raphson Method? 1685. Sure, all of you know that. I just touch it upon. It's a real valued function. If I want to find the zero of the function, x0 is your initial guess. Then x1 is x0 minus fx0 by f dash x0. Of course, with the assumption that f dash x0 is not equal to 0. And then the better approximation is this one, the general formula xn minus fxn by f dash xn. Right? So apply that to Bhakshali case. X square is a square plus r. That's the Bhakshali case, right? Apply the Newton-Raphson method on this case. The function here should be then x square minus a square minus r. And then your first approximation x is a, which is x0. And x1 will be, according to Newton-Raphson, x naught minus fx naught by f dash x naught. So if x naught is a, if x naught, you can easily calculate your x naught being a. If you put it here, it is simply minus r. So f x naught is minus r by f dashed x naught. So you do that here, it's twice x, and x is a, so it is twice a, and this minus and minus make it plus, and you see the first step of Bhakshali correction, a plus r by 2a. Go to the second step, x2, x1 minus fx1 by f dashed x1. Do the same calculation, and you lead to the Bhakshali formula, the second correction. Yes, of course, Bhakshali ends it here. Bhakshali is quite satisfied with the second correction, and Newton-Raphson goes on further in general. Of course, that's an advantage, that's an improvement. Is it not amazing to know that what Newton and Raphson achieved by calculus in 17th century was achieved in India some 1,500 years back? I just give you some other such references. I'm running out of time. Maybe I can take 5-10 minutes more to tell you just some glimpses of works of Aryabhata and Brahmagupta, which will motivate you, which will tell you, yes.
Sure, sir.
So just 10 minutes perhaps. So you see here, this is the kind of equation solved by Aryabhatta.
Sir, you are muted.
Hello, sir. You are muted. Please unmute.
Is it okay now?
Yes, yes.
Am I audible? Am
It is okay.
Yeah, okay, fine.
Yes.
Sorry about that. Okay, so the point I'm trying to raise now is, I'll give you a parallel chart kind of situation. It's really amazing to see that once this development was made in India by Aryabhatta, Brahmagupta, and so on, the others, as you can see, the Bhaskara 1, Mahabira, Govindaswamy, Pythagoras, Aryabhatta 2, Sripati, Bhaskara 2, Narayan Pandit. There's a long list of people working on this kind of things, Kuttaka, pulverization. And further developments on that led Brahmagupta to solve what is now once again wrongly referred to as Pell's equation. The whole story as if was staged again in Europe some 600, 700 years after. It's very amazing, really, really amazing to note. This equation, when Aryabhatta solves it, it's 499 that time, Kuttaka or pulverization. And these methods and its variants were discussed by so many mathematicians. The same method was rediscovered in Europe by Bachet in 1621. This, what is known as Kuttaka or pulverization in Aryabhatta's, you see, this is something which is wrongly referred to in international level of mathematics as generalized Euclidean algorithm. You won't find, I challenge you, won't find anywhere it in Euclid. It's nowhere in Euclid. But unfortunately, it is referred to as generalized Euclidean algorithm. This relationship between GCD of A, B, and C, the solvability of this kind of equation, and this ingenious method of Kuttaka based on that you make the number smaller, pulverization, break it up into smaller numbers and gradually solve it. It's a fantastic method. I don't have time to get into details. Amartya, that good friend of mine from ISI Kolkata, has good articles written on Kuttaka. If you're interested, can search them and read them in details. So once Bachet, 1621, just remember it, Aryabhatta did it in 499, and then you see 600, 628, and so on for almost 900, 800 years. There is a legacy of working on Kuttaka in India. When 1621 Bachet rediscovered this Aryabhatta's method in Europe, in 1798, within 100 years, Legendre, a great big name in mathematics, European mathematics, you are all aware of Legendre polynomial, etc. So he writes that Bachet solved the indeterminate equation of first degree by a general and very ingenious method. And Bachet work inspired Fermat, and Andrew Weil in 84 writes this: Bachet method for solution of the equation undoubtedly provided a model for Wallis, Brouncker, and Fermat to follow. Just like Aryabhatta's work, it made a beginning, which was followed by this Bhaskara, Brahmagupta till Bhaskara 2 and Narayana. Bachet did the same thing here, played the role of Aryabhatta here in 1621. Only the time, you see the time gap, over 1,000 years. And just after that, a flurry of similar activities is found in Europe by Wallis, Brouncker, Fermat. And here I come to refer to this fantastic composition law of Brahmagupta. You see, this problem posed later by Fermat, 1657. Fermat problem was this: nx square plus 1 equal to y square. It's a quadratic Diophantine kind of equation. You have to find integral solution of that, positive integers, solutions in positive integers of this equation. What Brahmagupta did in 628 was a much general version. Nx square plus z equals to y square. See, for Fermat, z was exactly equal to 1, special case. Brahmagupta did it in more general way. And he invented a kind of binary composition, which he called Bhavana. The principle of Bhavana, it tells that if you have one solution x1, y1, z1, all positive integers for this quadratic Diophantine equation, and x2, y2, z2. If you have these two initial solutions, then this composition x1, y2 plus x2, y1, n x1, x2 plus y1, y2, and z1, z2 will be a new solution of it. Just imagine, algebra is said to be developed by Arabians first. They are called the father of algebra. And here is Brahmagupta, some 300 years, 200 years before Al-Khwarizmi, is doing this kind of composition law, which is in spirit, not just algebra, but abstract algebra in spirit. I am not going to tell that, so abstract algebra was invented in India. No. These kind of things makes no sense. But this also doesn't make any sense that people of India should never know about the Bhavana principle of Brahmagupta. As you can see, that this principle defines a group structure. If you take this nx square plus 1 equal to y square and takes all these xy belongs to z cross z and takes this operation, the first two, x1, y1, x2, y2, the composition law is taken to be the first two of this Brahmagupta Bhavana principle, then this is a group operation. It doesn't mean that Brahmagupta knew about group. No, not at all. But look at the depth of their knowledge, the depth of their understanding. That's what I have been trying to tell you for last 1 or 2 hours. We must translate their work in the present day language and try to understand and appreciate how far they have gone, how deep they have gone, how was their idea of mathematics. That will be the real homage to these great minds. And you see, Brahmagupta gave examples. This was one particular example, very fascinating. 92x square plus 1 equal to y square. That particular one he solved himself by using his rule of composition. And you know, with this particular example, he proposed a kind of challenge. Purvanna vatsarad ganakaha. He was challenging his contemporary mathematician, where I give you 1 year time. If you can do it in 1 year, I will consider you to be a ganakaha. I will consider you to be a mathematician. Purvanna vatsarad ganakaha. Because he knew how to solve it by his ingenious Bhavana principle. I can show it to you here. See, 92x square plus 1 equal to y square. The perfect square nearest to 92 is 100. So you just write it as 92 into 1 square plus 8 into 10 square. So it is in this form, 92x square plus 1 equal to y square. See, that's the first step. That leads to this initial solution by inspection. So to apply Bhavana, you need to know initial solutions, x1, y1, z1 and x2, y2, z2. Then Bhavana says that you can make a new, you can amalgamate then in this particular rule of Bhavana, and that leads to a new solution. That's how you can have infinitely many solutions. But how do you get hold of an initial solution? That's the easiest way. The 92 x square plus 8 equal to 10 square, that's the equation you make. And then according to the Brahmagupta's nx square plus z equal to y square, nx square plus z, here z is 8, right? Plus y is equal to y square, 1, 10, 8 is a solution to this equation. Nx square plus z equal to y square. See, 1, 10, 8. So what you do is you take this solution twice. Nowhere it is told that x1, y1, z1 has to be different from x2, y2, z2. Look at the ingenious approach. You just take the same twice and apply Bhavana. This x1, y2 plus y1, x2 and so on. So what you get is this new solution, 20, 192, 8 square. So write that equation in this form. 92 into 20 square plus 8 square equal to 192 square. But you have to get to this 92x square plus 1, right? So divide by this 8 square to get 1 here. So you divide here. What you get is this. Well, still that cannot be a solution. 5 by 2 is not an integer because ultimately you want to have an integral solution, positive integral solution. That's what you can call a solution to this kind of equations. So what you do is you just take this 5 by 2, 24 and 1, this triplet, and apply Bhavana to itself. Once again, that leads to 120, 1151 and 1. And that is the smallest solution of this problem. 92 into 120 square plus 1 square equal to 1151 square. Amazing, amazing. If it is not genius, then what is genius? And the fantastic fact is that You see here this parallel. Aryabhata 499 solves this equation. Brahmagupta 628 goes to second degree. Dx square plus 1 equal to y square. Brahmagupta discovers composition law. Here, Bashe 1621 solves the same equation. 1657, Farma takes up dx square plus y equal to dx square plus 1 equal to y square. Both problems considered important in modern Europe. And in 1764, Euler, the great Euler, Leonhard Euler, rediscovered this composition law, the Brahmagupta Bhavana principle. This was rediscovered by Euler. The following problem was posed by Bhaskara II in 1150. The same problem was posed by Farma in 1657. 61 x square plus 1 equal to y square. That was 92. Comparatively easy, smaller solution. This one is going to be larger. The same problem, Bhaskara II in 1150. And it was done by a fantastic method called Chakravala by one Jayadeva, to whom Bhaskara II refers. Chakravala algorithm. And the same was done by Farma by his method of infinite descent, reaching the same answer, both of them. Only one in 1150, the other in 1657. See, that's the Chakravala algorithm. And the solution, the smallest solution to this is this. X equals to this number and y equal to this number is the smallest solution to 61 x square plus 1 equal to y square. And Euler rediscovered this Bhavana principle. And he called it, in 18th century, he called it Theorema Eximum, Theorema Elegantissimum, the elegant theorem. Rediscovering the theorem. Great men things alike. It will not be very justified to blindly say that so these people actually copied things from Indian mathematicians. If you have to tell that, you have to establish it. No point in making claim. It's a fact that there is an absolute similarity in the progress. Even the very same equation is being dealt with, but in a different way. So it's a question of research, whether there is a scope of this Indian knowledge reaching Europe by that period of time, whether they were actually inspired by this and then tried their own hand, or whether it was simply a blind copy. Let us not make conclusion here. Let us keep it open for further research. But the fact stands that what is being done here, as you can see in Europe in 17th and 18th century, was done much earlier in India. And after knowing all this, it will be very difficult to conclude in one line that the Greeks invented geometry and the Arabs invented algebra and India only invented zero. I would like to conclude with these great words of André Weil, a giant of a mathematician of 20th century. What would have been Farma's astonishment if some missionary just back from India had told him that his problem had been successfully tackled there by native mathematicians almost 6 centuries earlier. Thank you very much for your patient hearing. There's some of the references where you can have many more discussions of a similar type. If you are interested, make a copy of this, screenshot or whatever. There are many others. Of course, this is not a complete list, but thank you very much for your patient hearing. And I think I should stop here and allow some question answer session. Thank you.
Thank you, Professor Parthasarathi Mukhopadhyay sir, for the wonderful speech. I am sure that the input from your side on rich mathematics tradition of India certainly raised everyone's pride on the great culture and heritage of Indian mathematics. Now is the time for discussion and introduction. Parthasarathi Mukhopadhyay sir will be with us for some more time for attend your queries. I request to introduce yourself and keep your video mode on for asking your queries. Others are requested to keep your mic muted.
Hello sir, I am Diya Shah. I am doing MSc in mathematics. I am in first year of my MSc. Sir, this session is a great gives me a great view of the progress of the works in ancient mathematicians in India, and it is very inspiring to me also. And the comparison between the modern mathematics and ancient and the works of the ancient mathematicians are also very inspiring, sir. Thank you, sir, for this wonderful session.
Good afternoon, sir. I am
Good afternoon.
Shilpana. I am a first year MSc student. Sir, your session was full of energy and we were really glued to the screen for 2 hours. It was so nice. You took us through a journey, and it was so interesting to see how each and every small equation had a big story behind it, the story of a civilization. So thank you so much for this session. You inspired us to more into the subject. So thank you so much, sir. And I also thank Vinod sir for arranging this session.
Thank you for the wonderful presentation. I'm calling from Nigeria.
Thank
It's
you.
a great presentation. I have learned a lot, and I've got a new idea. So many things I did not understand before, the way I understood today. But I also want to request for the presentation material, if possible, for the PDF for consultation. Thank you, sir.
I'm an alumnus of IIT Madras from 1975. I've been
Yes.
teaching mathematics to school students, and now in my late 60s, I'm getting a chance to look into such beauty of mathematics, especially Indian mathematics. I've been reading quite a lot, and also trying to introduce this to school students in a small way. What professor has explained in this 2 hours, it cannot be done in a single sitting for school students. So we can introduce them whenever you introduce a topic, say Pythagoras theorem, you can just bring in this Indian mathematics, also the history of Indian Pythagoras theorem, so that children will get motivated. I think that is also going to be the new national education policy. So that way it has benefited me a lot, and very interesting. I could follow that, and the explanation in Sanskrit, it was very beautiful. I would like to go over it again. As you said, if you share the video, it will be very useful to us. And thank you for organizing this. Thank you to Professor Mukhopadhyay.
Sir, my name is Nandana K. Vasudevan, and I'm a research scholar at Amrita Vishwavidyapeetham, Coimbatore. To be frank, I don't have much idea about this Indian mathematics, like its historical side and all. So for a person like me, your session was highly informative, sir. I have never taken much effort to look behind what is going on in mathematics during these olden times. So your session was really informative, sir. Thank you for your time. All the students, I think all of them, including me, it will be a great session to understand the history of mathematics. Thank you, sir.
Thank you.
Hello, I am Anindo Dev from Hindu School, Kolkata. My question is that is it common that all the proofs of the works of the ancient Indian mathematicians are not available, or otherwise some of the proofs are available?
I understand. The idea, as I told you during my lecture, the idea of what is called proof, quote unquote, that is accepted nowadays worldwide as the formal way of presenting an argument which can be accepted as a proof in mathematics, it was not found in ancient India. Ancient Indian mathematics, their way of doing it, way of looking at it, and way of establishing the fact was a different one. If you want to look at the Indian mathematics with an intention to find a proof of this Greek style, you can never find it. It's not there. But that doesn't mean that they were unaware of the proofs in the sense of English, that they only, vaguely have written something which they were not sure about their validity. That is not the case. This validity were established in different way of, different genre of thinking. One of that is called Upapatti. One other is there in Bhakshwali Manuscript. These were a different kind of way of looking at it. Of course, that way nowadays in the modern mathematics perhaps will not be accepted as a valid way of proving things. That is one very important point. But the other side of it is, because the modern mathematical way of proving things cannot be found in this ancient Indian part of mathematics, immediately you claim, so there was no proof in it. They didn't know the proof of that. Now that will be a gross injustice. You have to study a thing, particularly these kind of ancient things, as they are, in their spirit. Just like I tried to explain that had it not been the convincing idea of the result of so-called Pythagorean theorem that we find in Bodhaya and so on, were they not convinced somehow that this is universally true, they could not have applied it to general cases as they have done in several other sutras. That shows that they had their own way of satisfying themselves about the validity of these statements in general. There's one word there in the definition of sutra, as I told you, universality. Vishyato mukham. So that universality is in spirit the idea of a theorem in modern day mathematics. That when you say something is a theorem, just like Pythagorean theorem, you claim. Why is it a theorem? Because every single right angle triangle have to abide by that. There cannot be an exception. Then it would not have been a theorem. It would have been, because you have a proof of it, logically. And this proof is not to be done by numerals, that you make one by one after one, several triangles and verify and say, that's a verification. That's the modern approach difference between verification and proof. The Indian way of doing it was something different. Whole details is not known, unfortunately, because that's the impediment always with ancient India, that there is no written texts. What exactly was discussed in that one-to-one situation in the Gurukula, that has gone missing. Even today, I make a conjecture of that. There is no way I can make that acceptable worldwide to everybody, because there is no written record. That's the most unfortunate part of the ancient India, but that is ancient India all about. If you initially say that because there is no written record, I am not going to call it history, then you have to simply set aside India and talk about the Mayan history, the Egyptian history, the Babylonian history, and then there is no history in India because there is no written record. That will be gross injustice to a civilization which scaled such lofty heights in several disciplines of human knowledge. So there's a requirement of looking at the thing the way it is. That's the point.
My another question, as Ramanujan said that he got his mathematical insights from Devi Namagiri. Is there any clue how they got it?
No, actually, you see, it is said, this statement is a very famous statement of Ramanujan, that for any equation has no meaning unless it expresses the will of God. Ramanujan at that point of time initially was a devout Hindu. He was a very devout Hindu and coming from a family which was very, rigorously Hindu practicing family. So it is very natural that's in the Hindu culture itself, that the devout Hindu never claims things to his or her own excellence. He always says that it comes from the grace of God. That's a way of saying. That doesn't mean that God himself or herself comes and tells me the result and I just copy it down. That's not to be, understood in the literal sense. When he says that I get it in my dreams, now you know what people dream about. People dream about certain things that he thinks 24 hours, where he lives mentally. That's what he dreams. So Ramanujan used to dream of mathematics because he used to live in mathematics. Every time he was thinking of that. So it is perhaps not right to take that in literary sense, that he got it from Namagiri, in the sense that the Lord Namagiri actually, dictated the results and Ramanujan only noted that. If had it been that case, then you would never have seen Ramanujan working tirelessly, hours after hours, days after days, months after months, working on that. This is his own working. He got the thing himself. But as a devout Hindu, that's a way of placing everything to the grace of the Almighty. That's what it appears to be.
Hello, sir. I am Chitram Banerjee and I study physics in IISER, Kolkata. So I have two questions. First of all, I have to thank you for this illuminating presentation and the session overall. I have two questions. The first is often we have this Eurocentric versus Indocentric people clashing about whether Greek people invented it first or the Indian people invented these things first. But I often wonder if there has been a much more collaborative effect. That means Indians inventing things and that being transported to Greeks. As we often know, there were definite trading routes working between both in the landmarks and in waterways. So if there has been this kind of collaboration, and how well studies is that?
Well, these are being studied. There are people who studies this collaboration, this possible transmigration of both ways. It was not just from one way to other.
Sure.
Came from Greece to India. Things have gone from India to Greece via Arabs. These routes were there, and this is how the things got mixed. And as far as personally I am concerned, it is not very important to actually highlight this priority issue that who came first. This
Right.
second issue is not. It's as far as I am concerned, a bit childish in claims that I am first. That is not important. The important thing is to know exactly what was there, how and when. What I find objectionable is to suppress certain fact to establish the other part. That is not right thing to do. People in academia should have open mind. And there will be always in this kind of forum, in this kind of discussion. You see, it's not like mathematics that 2 plus 2 in decimal system has to be 4. Whenever you are talking about this mathematics, history and other things, there will be objections. There will be people who think this is right. There will be people who think that is right. There will be controversies. It will be. It can never be ultimately settled just like 2 plus 2 equal to 4. But that should be welcome. The fact is, 1, 2 is there, the other 2 is simply not there. That is not a welcome situation. Unfortunately, that's what we find in India. But somehow, because of different reasons, I'm not getting into that,
Yes.
for a long period of time, Indian history was not written by Indian historians.
Yes.
It was written by others. And as they have done it according to their own choice, according to their own schoolings, their own bias or whatever, that
Yes.
has been taught here as Indian history.
Right.
The backlash to that, what is happening now, is unfortunately equally bad. It's a kind of backlash, Newton's third law kind of thing. Now there is a kind of thing that everything was there. It has to be just everything. Nothing can be spared. And you have to say that everything was here. That
Right.
again is ridiculous.
Yes.
That again is ridiculous. There should be some objective study of what is what. And only academic people should talk. Other people, political people and other people, they must have their own business. They must have their own interest. But they should not actually judge or decide that what is what. That is very unfortunate state of affair.
Yeah. Yes. Thanks. Thanks for the clarification. Actually, I have a second question because I myself am a Bengali, and I am amazed that there are such wonderful research books, in fact, which are written in Bengali that I can have access to. My question comes that, like you said about Bodhayan's Shulva Sutra, there was also, because I'm a student of physics, there was Kannada's Vaishashik Sutras, and these I have tried to read some Sanskrit and some English translations done by Dr. Subhash Kak. But I'd be delighted if I could find, or you could point out to some resources where I could read in more detail about the definitions and more discussions in Bengali?
Unfortunately, as far as I know, there is no such general trend of writing such things in Bengali. Almost 99.9% literature that is available is in English. So that's one of the reasons that I have started writing things a little bit that I can in Bengali. Vaisheshika Sutra, I have read certain articles here and there. One gentleman is there in IISc Bangalore. I have met him over net few times in last year only. But his writings are very impressive. He's from chemistry background. He's Mr. Amitabh Pramanik, right? If you can keep in touch with him, he happens to have studied seriously these kind of things, and he writes a lot in social media from his own perspective. And I think he can give you better insight of this kind of. My writings or study is very, very limited to mathematical part of it. Physics is something that I don't understand much myself. So, of course, though I am aware of this kind of Vaisheshika Sutras and Konad and all such things, and again, claims and counterclaims and some inflated, meaningless claims, everything is there, just like in mathematics.
Yes.
So, objective studies require, real scholarship that will tell you exactly what is what. And that is not done. That is usually not done. So, this requirement is there. Young people like you who are interested, it's a good thing to know that young people are taking interest apart from, just like you see, people like me. I don't do history of mathematics for earning my bread. I am a teacher of mathematics. I teach abstract and linear algebra. And I do like that. But this is something which I do parallel to itself. So young people like you, researchers who are doing mathematics or physics, just as a parallel study, should also try to know and unearth, and at a point of time should start writing some things for general mass to make them aware of what is what. Otherwise, this field is going to the hand of should I say uneducated people who are trying to say every kind of nonsense and mumbo jumbo, and thereby making more damage than good to the cause of ancient Indian science.
Yes. Also, just I don't know if I am lengthening the time stretch that I shouldn't, but I just wanted to point out that except the study of history and being amazed about how far we could move, it's also important sometimes, for example, from this Vaisheshik Sutra, it actually gives a different perspective to the world, which probably we are kind of indoctrined by learning in the Western ways. And I'd say like only one specific way. It probably gives help to people who researchers or anybody else to shed new lights into the thing. So that's all I wanted to add. Thank you again for your.
It does. Thanks. Nice talking to you. Thank you.
Good afternoon, sir. Myself Anisha, and I completed MSc from Kerala. The class was very nice, very informative for us, and I think it was the first time I'm hearing about this ancient in mathematics, and it was very surprising for me that all these things was invented earlier. So thank you so much, sir. And your voice was very nice. That keep us very active in all these throughout this lecture. So thank you so much, sir. Thank you, Vinod sir, also. Thank you.
Good afternoon, sir. Myself Lakshmi. I am from Kerala. I am a third year basic student. Sir, your session was very informative. Through this session, we were able to understand the ancient Indian contributions towards many mathematical concepts which we learned today. So it was very nice and wonderful session. And thank you so much, sir. And also, I would like to thank all the persons who worked behind this webinar. Thank you so much.
Myself, Jish Shahani, sir. I am from UP, but recently I am pursuing my MTech in electronics design and technology from Teshpur University. I want to ask you something, sir. It's really helpful for me in my field also, sir. It's also reliable for me in my field. On working on that, so I want to ask you, sir. Recently, I'm pursuing my MTech electronics and electronic design and technology, sir. I want to ask you something regarding this Indian Indian ancient mathematics. It's a really useful tools for me. It's a really
No, no, I'm afraid no. Your modern day technology, etc., the thing you are pursuing, these are all different things, new things. Uh, per se, there will be no direct application of what is there. It's modern mathematics and modern science is good enough for your branch of knowledge to pursue and master. These are something that their values. The values of this thing, as I have pointed out already, are inspirational.
right.
That you belong to a race that once scaled such height. If that inspires you to rescale that, to go beyond that, that's the purpose of this.
Okay, sir. Okay, sir. Oh, thank you so much, sir.
The session was really wonderful.
Thank you.
I'm Bhavya. I'm pursuing currently MSc Honours Mathematics from Punjab University. I really learned a lot of things like how to adjoin squares, n squares of equal side into a larger square.
Thank you.
Finally, we are now reached towards the end of today's session. I invite Miss Amrita Warrior from St. Joseph College, Devgiri, Calicut, Kerala, to express a formal vote of thanks. Over to you, Amrita.
Good afternoon, all of you. I'm really happy to be a part of this webinar and also a part of the organizing committee. Let me begin with thanking Vinod sir, Associate Professor at TMG College, Tirur, Kerala, and also Dr. Bijumon sir at MG College, Irati, Kannur, Kerala, for organizing this wonderful session by Parthasarathi sir. It was really an informative and also inspirational session. And also I would like to thank Ambat Vijayama sir for introducing our speaker. Next, I would like to thank Dr. Parthasarathi sir, Associate Professor of Mathematics, Ramakrishna Mission Residential College, Narendrapur, West Bengal, for taking this session on glimpses of ancient Indian mathematics. To be honest, when we think about mathematics and mathematicians, Indian mathematicians won't come to our mind. It's true for everyone, including me. But you told us about a glorious and also a little more unknown past, about our ancestors who had many more contributions to mathematics, which has been unknown to us, especially in the case of Pythagoras Theorem and even Fibonacci sequence and all. Thank you, sir, for all the informations. And also about the zero, one of the most enigmatic number. And you also told about the approximation of square roots and also relation with the Newton-Raphson method. Right now we are learning it, and it's really astonished to know that it has been told something, or it has related to something with Indians. It's really inspirational that our ancestors has done so many things, but we in our blood it is there. As an Indian, in our blood it is there. So it is really inspirational. Thank you so much. I, on behalf of everyone who was present in this class, I thank you so much. And also I thank you sir, for sparing your valuable time for teaching us so many things. It's really unknown to all Indians, and we always go behind all other people rather than knowing what we are, rather than knowing our past and all. Thank you so much. I would also like to thank Ms. Gia Rose, a research scholar at IIT Madras, and Ms. Anne Mary, a research scholar at CUSAT, and also Namrata from MIT Karnataka, and for organizing this webinar along with Vinod sir. And I would also like to thank Ms. Titi Bishwas for arranging and for her wonderful coordination throughout this webinar, and Ms. Anjali from Cochin University for her prayer. And last but not the least, I would like to thank each and every person who were being in this webinar from the beginning. Thank you so much, and thank you, sir. We are so blessed to have you on this day. Thank you, sir.
We are winding up now. Once again, thanks to all for being with us. Have a nice day.